Okay, welcome back everyone. In this video I'm going to do a quick example problem of how to work with magnetic fields and forces. And so this is from chapter 27, it's problem number 74. So what we have is a portion of a track. This is actually um, kind of what you think of when you hear the word railgun. So you have a rail that kind of continues on for a while that carries current this direction. So kind of goes like that. And we're also given that we have a mass of m and we have a length of L in between these two rails. And just to make it a little bit easier, I'm going to make my axes kind of like this. So kind of, coming this way towards us is going to be x-axis and then y and z. I think that satisfies our rules. And in part A, what we're trying to do is to calculate the net force on this little bar that I've masterfully drawn here. And so the net force is going to come pretty much from the magnetic force, and so it's going to be IL cross B. And because we're dealing with a constant field that's directly upwards, kind of in the B direction or in the Z direction, okay? So we'll just call it some random value B naught Z hat. Since the magnetic field goes that ways, the current is constant and L is constant. The force is going to be ILB, and we'll say it's in the I hat direction. So the force is going to cause the rod to move this way. Now you might be wondering about gravity or things like that. We're going to assume that there's a gravity force in the negative z direction and then an accompanying normal force in the positive z direction, and those are going to cancel out. So the net force will just be the magnetic force in the x direction. Now in part B, we're asked to find the acceleration, and because the force is constant, the acceleration is just going to be the force divided by the mass. And we also know that the distance it travels from the equation v final squared equals v initial squared plus 2a delta d. The distance that it travels, say v initial is 0, is going to be v final squared over 2a. And this is going to be, if you look at the expression for acceleration and you plug it in, it's going to be m v final squared over 2 I L B. And if you want to see something kind of crazy about this, since we're dealing with all sorts of constant values, remember our work energy theorem? So work is equal to a change in kinetic energy, right? But the kinetic energy is 1/2 mv final squared. And sure enough, if I look at my force, ILB, and my distance d, the work is going to be the force times the distance, and that's going to be mv final squared over 2. So this is just another instance of the work energy theorem. Okay, now finally, in part C, we actually want to plug in numbers for this, and we're given things like the mass is 25 kilograms. We're given that the current is about 2,000 amps, which is a lot of current. That would take a huge amount of power. Let's say that we have two rails that are a half meter apart, and we have a magnetic field that is 0.80 Tesla, which is not too horribly difficult. And let's say that we want it to reach escape velocity, which is 11.2 thousand. How long would this railgun have to be? So we take everything and plug it in. So D is equal to mass times velocity squared over 2 times the current times the length of the rail, in other words, the distance between the rails, times the value of the magnetic field. And what we get for this distance is about 1960 kilometers. So, in other words, just to get a small object, 25 kilograms is not that much, to launch that into orbit or to escape the Earth's orbit, we're talking almost 2,000 kilometers. So that's a sizable chunk of distance. But hopefully you see how to apply the rule for finding magnetic forces. We're using the right-hand rule here. And just as a reminder, the reason that I knew that the force was in the x direction is that I'm doing IL cross B. And so in this case, I'll see if I can draw this in green right here. Uh, Going across that rod, I is in the y direction, and B is directly upwards. And so when I do the right-hand rule with that, my thumb is going to come out of the page towards me, so that's how I know that the force is outwards. Okay, so that wraps it up for this example, and we'll see you next time.